Hi everybody. So I will present you the solution of the old memories challenge. This was a challenge divided in 9 different steps. There were 5 Ordinosaur steps, we will see later, and 4 technical steps. So each Ordinosaur steps was separated by a technical challenge. So this was the first challenge. We were only given this picture, and we had to find which computer it was. So this one was a Thomson MO5. It was possible to find it by looking at the RAM cartridge and then Googling the text on it. Second step was the first technical step. So we were given only a domain name and a port number. Port was port 70, and this is the default port for the Gopher protocol. This is the ancestor of the HTTP protocol. So when you connect to the server, you can do a directory listing with a slash. Then you find some files. One of the files is cwe22.txt. And it is the definition of a path traversal vulnerability. So, well, by trying different things, we finally find we can perform a path traversal with // etc password. And then we can so read the password file and find the first flag, which is in green. And for the record, the Tomomis bota is this animal. Step 3, it's another Ordinosaur. This one, so we have, for each step we have a hint. So the hint here is Hartmut Elslinger. And so the computer is the Apple IIc. And Hartmut Elslinger was the designer of this computer. Step 4 is a forensic step. So it's welcome to 1985 forensic. So we're given an OVA file containing a VMDK. We can convert the VMDK to a raw file using QEMU IMG. And we find that this image contains a DOS. So it's a DOS version 1. We can even boot it with QEMU. If we start looking at the image, we find quickly a file which has been deleted. In FAT16, the first character of the file name is replaced by an underscore when the file is deleted. So, well, given the name, it looks like a flag, so we can extract it, then look at the file header. File header is .m, and by Googling it, we find that it's MS Paint 10 image format. So now we have to be able to read it. And thanks to Google, we find a Python image library plugin, which is called MSP image plugin, which allows us to convert an MSP file into any image format, so we can have the flag and a beautiful picture. Step 5, another Ordinosaur. This one is a Matra Hachette Alice. The hint was MC6803P, which is the processor used in this machine. Step 6. Step 6 is what the fuck barbecue code, which resumes the challenge. So we are given an archive containing an encrypted zip file, an AES encrypted file, and a PNG file. This is the PNG file, and it's definitely not a QR code. By looking at it, we can see that it seems to be slices of common barcodes. So what we have to do now is read the EAN13 standard, which is the standard for the barcodes, write a decoder, and try to decode each line of the pictures, and hoping we get something. So we can see that there are only 6 different lines, and only one can be decoded by this method. So it decodes to this value. By a little bit of guessing, we can open the zip file using this as a password. And in the zip file, we have 6 barcode images, which are in fact the 6 ones which have been sliced before. And it, it also tells us that the AES key to decrypt the last file is the combination of all the barcode values. And we also are given hashes for each barcode value to help us know if we have correctly decoded it. But we still have a problem, which is that we can only decode the one barcode. All the other ones seems to be invalid. So we now have to somehow guess how to fix the barcodes to be able to decode them. And well, by trial and error, we finally find the modification to perform on each barcode to be able to decode them. So the first one was okay. For the second one, we have to perform a rotation of all the bits to have a correct barcode. For the second one, we have to apply a knot on the bits of the second part. Number one is fixing first digit. Number 4 is fixing checksum. And the last one was a bit what the fuck barbecue, and we had to try to fix each digit one by one. And in the end, we have the AES key allowing us to decrypt the flag. I hope you like this one. Step 7, little brother. So, well, when I saw this picture, I thought it was a Commodore 64, but there was a hint, little brother, so this isn't the Commodore 64, but Commodore VIC-20. I didn't know it. Step 8. So this is the reverse part. Memory-based register, MBR. So we are given MBR to reverse. So this is 16 bits code in real mode. When we first look at it, we can see that there's a XOR loop at the beginning, which decrypts the next layer. We can easily script IDA to do the decryption for us, and then we face this. So a big bunch of pushes with a far return in the end. So this is in fact ROP, return-oriented programming, in real mode. So what we have to do now is take each of these values 2 by 2, because the far return instructions grab the 2 values on the stack, one for the IP register and one for the segment. So we grab the value 2 by 2, we compute the value segment multiplied by 16 plus the address. We try to find the basic block corresponding in this address, and then we can also fix the add SP, sub SP instructions by replacing them by jumps. And finally, we can have a clean code. Well, I don't think you can read it, but it's clean. So after that, we can begin the analysis. So first, there's a password prompt to the user. Then we have a bunch of obfuscated code. There's, for example, some push and pop instructions which have been emulated because as we are executing a ROP, we can't really push and pop values. Okay. Good. Good. Ah. Tu peux remettre en plein écran? C'est bon. Merci. Okay. Okay. Yes, there are pop and push instructions which have been emulated because as we are executing a ROP, if we are pushing on or popping values on the stack, we break the ROP chain. So there's an alternate stack which is created, and then, for example, this is a push instruction emulated. There are also some many useless instructions, so we don't know right now what this code is doing. After this code, we can see some transformations on the password entered by the user. It's first XORed, then it's stored 3 bits by 3 bits in an array, and it skips some indexes in the array in which there are already some values. And finally, it prints the bad boy message, so telling us that we lose. So, well, that's a bit weird because there hasn't been any check on the password. So if we trace the code a bit with the QEMU, we can see that in fact there are instructions executed before the bad boy printing. So it seems that someone has been hooking the int10 instruction. So it might have been done in the big obfuscated code. And if we look at the hook function, we can see a new wrap chain. So same operation, we clean it and we have a code which can be readable. So what does it do? This code will check the arrays that has been previously filled with the password, transformed, etc., etc. The size of this array is 9 by 9, and there are checks that only one occurrence of each digit between 0 and 8 occurs for each line, each column, and each 3 by 3 square. It's a Sudoku. So we can retrieve the value and extract the Sudoku. And we can solve it. And once it has been solved, we just have to revert the algorithm, the XOR, and then we get the flag. Then, final step, the last ordinosaur. So this one was quite hard to find. It took me 30 to 40 minutes Googling to be able to find it. So the blue color can help. We know that it's the IBM color. And then by looking at many pictures of old IBM computers, we finally find that it's IBM 1130. And that's all. Thank you.